Okay, so welcome to the first of my webinars on modern Java in practice. We're going to get started here in just a second. The basic idea of this webinar series is to have me walk through examples from my live lessons repository, which is a GitHub repository I'll show you in just a moment, and kind of take some time to really step through them in detail. If you have questions, please feel free to type them into the chat window, and I will stop periodically and answer questions. Let me first tell you what this session is not. This session is not intended to be a comprehensive soup to nuts tutorial on every aspect of modern Java. I will point you to some resources that give you a lot of that kind of information, which you can watch at your leisure. This session is really, or these sessions are really about walking through examples and showing you how you develop code using modern Java features, both in the programming language as well as in the class libraries. So with that, let me go ahead and share my screen. And let's see, I think we can just go ahead and start by sharing the web browser. I think that's probably a pretty good place to start. And let's see what comes up here. So if you go over here, hopefully you can see my screen. This is the digital learning webpage I've got where I have lots of content. If you want to learn more comprehensively about modern Java, I have hundreds of hours worth of tutorials you can go watch here. These are all the recordings I do. I do screencasts of all my courses I teach at Vanderbilt. You can go and take a look. It's all there for the past 7 years or so. So feel free to take a look at that. There's other material here as well we'll talk about later. I also put up a little community tab on my YouTube channel asking what topics people would like me to cover. So that'll help provide my focus over the next days and hopefully beyond that for this type of stuff. Let me also show you something else too. Let's go ahead and open up a new tab. If you go to my GitHub repository, which is at this link, and you click on the live lessons link, then you'll see I have, again, dozens of examples for modern Java. And what I'm planning to do is I'll update my website here, which is the Modern Java by Example webinars. I'm going to update this to indicate what topics I'll be covering over the next few days. So after today's session, I will go ahead and update this to indicate what I'll do tomorrow and Wednesday and Thursday and so on. And that, of course, will all be based on the feedback that I get from my poll. So feel free to go over and vote for what you'd like to see. And then I will go ahead and cover those topics, and I'll prioritize it based on what you're most interested in. So if you take a look here, this is where all the material is going to come from. It's basically going to be from the material on my GitHub account, which is right there. And there's lots and lots and lots of stuff, as you will see. What we're going to do today is we're going to start off by talking about the RxJava EX2 example, which you can get here. And of course, I suspect you all know how to get access to this stuff. You can just go over here and you can clone my repository, and you can get access to all the software. So with that, let's go ahead and stop sharing that part, and let's go share my IntelliJ. So this is the project. I've opened it up in IntelliJ, which is my preferred Java IDE. Depending on what we talk about, I also may talk a bit about some of the Android Studio projects as well, and we'll get a chance to play around with those. So this is the program we're going to look at today. I ran the program earlier, takes a little while to run, and I put the output down here. And so we'll come back and look at this in more detail as we start looking through the various examples. So let's go ahead now and start looking at the code. So this program is designed to demonstrate how to download images from remote web servers using different mechanisms, including Java parallel streams and also including RxJava. And we'll take a look at the source code here in just a minute. And then it also goes ahead and compares the performance of Java parallel streams and RxJava both with and without using the fork join pool managed blocker interface, which is a means of being able to automatically expand the number of threads that are in the Java common fork join pool. Now, if some of these things are making no sense whatsoever to you, if you don't know anything about modern Java, if you don't know anything about Java parallel streams or the fork join pool or the common fork join pool, don't worry, I'll explain those things as I go through the tutorial. If you're looking for more comprehensive discussions of this, however, take a look at my digital learning website, and I'll go back and actually what I should do is probably put that into the chat session. Let me go ahead and put that link into chat so that you can have access to it. Let's see, let's send this to everybody. And if you go here, this will be the location of my digital learning website. So feel free to go to that link. That has the link to everything that we're covering. And there's extensive material in a course I taught in the fall of 2019, which covers parallel functional programming with Java. So feel free to take a look at that, and I think that will help you if you need to learn more comprehensively about these topics. But I'm going to just zoom in on an example. So here's the example. Obviously, we need a main method. You probably all know that. We go ahead and use an option singleton to parse the command line arguments and set debugging flags and anything else that we care about. I'll talk about that later. And then I go ahead and make myself a new instance of this class, and I run the run entry point method. So here's the run entry point method. And you can see what it's doing here. It's going ahead and it is essentially going to first warm up the thread pool, and we'll talk more about that in a second. That basically makes sure that the tests are going to be on an even footing because we will have pre-spawned some threads in the fork join pool. And by default, we're going to use the default number of threads in the fork join pool. Fork join pool is a mechanism that's part of Java 7 and beyond. It allows you to have pools of threads that are implemented using very clever techniques like work stealing and other interesting ways of trying to keep the CPUs maximally busy. And the common fork join pool, which is what we're using for these tests, has one less than the number of cores, and then it also borrows the thread of the caller. So you end up using all the available cores. And in fact, if you come down and you take a look at the little test program, when I ran it, it's a little hard to see this perhaps. It'll be easier to see in the video that I post to YouTube later. You can see how I have 8 cores on this particular platform. So it's a quad-core MacBook Pro with hyper-threaded cores, Intel cores. And so it has 8 cores, at least it thinks it has 8 cores. And you can see we're going to run different tests. And the initial test we're going to run will use the default number of threads in the fork join pool, in the common fork join pool, which is 8. And then we'll see how we're going to use the manage blocker mechanism, which I'll explain more in a second, in order to be able to increase the number of threads in the common fork join pool dynamically to resize based on the number of images that we're actually downloading. And then we'll come back and see how the different approaches compare and contrast from a performance perspective. So let's take a look at the overall structure of this. After we warm up the thread pool to make sure the threads are warm, we're then going to go ahead and run 4 different tests. The first test we're going to run here is going to use the so-called default download and store method reference. This is a method reference, which is a cool Java 8 feature that's kind of like C++ pointers to static member functions. And we're going to run this test, and we're going to call it the default download behavior as a string. And this is going to use the default behavior of the Java fork join framework, which will not add any new worker threads to the common fork join pool when blocking I/O occurs. And that turns out to be problematic because we will end up having blocking taking up the threads in the pool when, in fact, having more threads to run will make the system be more efficient, because while those threads are blocking, then other threads can go ahead and run. And we'll take a look and see how that actually influences the runtime performance in a minute. We then go ahead and run another version of the test. We're running these tests in a apples to apples comparison style way. And this is going to use the Java fork join framework's managed blocker mechanism. And I'll show you what that looks like in a minute. But basically what that does is it's a very clever feature added to Java 8 and the common fork join pool that allows the thread pool that's created by the common fork join pool to adaptively expand itself as the demand increases. So as blocking operations occur, the thread pool will automatically expand the number of threads to make sure that there's always ability to run new threads when other threads block. And so we call that the adaptive MB download behavior. We then run another test, which is very similar, except instead of using the managed blocker interface directly, which as you'll see is a bit cumbersome to program, we're going to use a really cool little wrapper or a facade for the managed blocker mechanism. And this is going to be called the blocking task, which is really cool and greatly simplifies the programming. So we'll take a look at that in a second as well. This approach under the hood uses the managed blocker mechanism in the fork join pool to add new threads to the underlying common fork join pool. All of the tests so far, as we'll see in a moment, all use parallel streams, and I'll show you how they work. The next test we're going to run is going to use RxJava, and RxJava is a set of extensions, the reactive extensions to Java, which allows for reactive programming using asynchronous functional programming style. And this will be kind of fun because it'll give us a chance to literally compare and contrast using parallel streams and its style of programming and RxJava and its style of programming in an apples-to-apples way. And you'll see that the actual code looks very similar, although surprisingly enough, the performance is somewhat different. And you'll see that when we get to that in a second. When we're all done running all these tests, we go ahead and print out all the results. And as you can see here, if you take a look at the results here, it sorts them from fastest to slowest. And we'll talk about the results and why the results are the way they are in just a minute. Okay, so without any further ado, let me start getting into the actual test programs. These are very clever little test programs where we have a method called runTest that's parameterized with a function. A function is a so-called functional interface, which was added to Java 8, which has a single abstract method. In this case, the method's called apply. And this allows us to parameterize the function under test here. So what we're going to do is we're going to take the function that's passed in, which is going to map a URL to a file. And then we're going to use this really clever little helper class I wrote called RunTimer, which is going to go ahead and run this function. And it's going to go doing it by calling this helper method called test download behavior, passing in the designated function and the name of the test. And then we're going to go ahead and record that in a hash map, which we'll talk about later. And every time we run a test, it's going to record the name of the test and the time taken to execute the test. And then we can print out the results when we're all done in a nice apples-to-apples way. You'll notice before we run the test, we first run the garbage collector to try to give a chance to start off with everything in a pristine state. My computer has 16 gigabytes of RAM, so it's got a fairly large amount of memory, and I don't think it's really a memory-bound test for that matter. We then have another helper method called runTestRx, which does the same thing, except it's going to use the test download behavior Rx driver. So it's exactly the same as the version up here, except this version uses parallel streams, and this version uses RxJava. All right, so let's take a look first at the parallel streams version. And this will give me a chance to kind of talk about parallel streams a little bit. Again, this is not intended as a parallel streams tutorial. I have hundreds of hours worth of stuff on tutorials of these topics. So you're welcome to go and take a look at the parallel streams tutorial and the streams tutorial and the fork join pool tutorial and so on. Lots of material there. I'm just focusing on a code walkthrough today. So the first thing we do is we delete the images that might have been downloaded from previous runs. And then we're going to go ahead and we're going to get the list of URLs to download. And this URL list is over here in the options class. And I have a whole bunch of files. You can see it's quite a large number of files that are available in my directory here at my website. I have a bunch of images. You can download stuff from there. I just use this as a place to get test images. And that's all part of the options singleton. So let's pop back over to here. And you'll see that we take this list of URLs and then we convert it into a parallel stream. And this is a really cool, magical process I absolutely love parallel streams. They're so easy to program once you understand Java streams. So we take that list of URLs and basically each URL on the list, and I've got something like 42 images that I'm downloading or so. I'm going to go ahead and have each of those things running in its own task, which will be mapped to its own thread in the common fork join pool. And this is really clever and really cool. We'll see how it works in a second. And by using parallel stream, that converts the list into a stream. And so you can see we take a list of URLs and convert that into a stream of URLs. And those are then going to be partitioned out into the threads that are available in the common fork join pool, which we can resize, as we'll see shortly. We then go ahead and run the download and store image function, which can be parameterized to either not expand the pool of worker threads in the common fork join pool, or to expand it with various techniques. So you can see we have this wonderful apples to apples ability here because we keep the parallel streams code identical and we pass in the function that we're going to use, which again, if you look up here, could be the one that doesn't do anything to expand the size of the pool, the one that uses the manage blocker interface directly, the one that uses the blocking task function directly, and so on. Okay, so the map method will then also be running in those different tasks, running in the common fork join pool threads. And that will go ahead and download the image from the remote server and then convert it into a file and store it in the local file system. And the final thing we do here is we collect the results of the stream, and this is going to be done in kind of a join-like mechanism. We're going to collect all the elements in the stream, put them into a list, which is implemented in the backing store as an array list, and that's going to be stored here in an image files variable, which is a list of files. So this is a classic example of the split, apply, and combine paradigm. Parallel stream splits up the input into parallel chunks. Those chunks then get run or applied in parallel in threads in the common fork join pool, and then the collector will merge everything back together when we're all done. So split, apply, and combine or merge. And again, if you watch the parallel streams tutorials I have, you'll learn everything you could possibly want to know about all this. The last thing we do is we print some statistics that basically say, for this test, we downloaded this many files. And this is what it says. You can see it says test default download behavior, downloaded and stored 42 images using 8 threads in the pool. So that's what gets printed by the print stats method here. And we'll come back and look at that more in a second. Okay, let's now take a look at the test load download behavior Rx method. This is doing the same thing, except it's using RxJava. Now, once again, it starts out by deleting all the images that were downloaded before. And then we go ahead and we're going to use RxJava features. Now, RxJava is a set of enhancements to Java, originally came from the .NET world, believe it or not. And the guy who developed this was a guy named Eric Meyer, who used to be at Microsoft. And now I believe he co-founded or founded a company called Applied Duality, and they promote RxJava. RxJava is really intended to be able to deal with event streams. And streams of images are sort of an event stream, but better event streams would be things like Twitter feeds or mouse movements as you're moving your mouse across a GUI, or stock information if you're doing online stock trades and so on. So it works okay here, but it's not 100% what it's designed to do, but it certainly does work for this. And so what we do is we go ahead and use a factory method called fromObservable, and we give it an observable, and the observable, of course, in this case, we give it an iterable, and the iterable in this case is going to be the list of URLs. So we take the list of URLs, which were the ones I showed you before, that were the images that are stored on my web server. Okay, so let's zip back over here. So we take that list of URLs, and that's an iterable, because, of course, a list is an iterable. And Observer converts this into a stream of observables. And that's the basic concept in RxJava. There's lots of different things there. At some point, I hope to do a longer tutorial about RxJava, but in a nutshell, basically it's a stream of observables. So think of it kind of like the Gang of Four observer pattern or the POSA1 publisher subscriber pattern. You have something that emits events, and then you can have filters and transformers that are used to modify the event stream. And then you end up being able to subscribe to those events. And we'll talk more about that in a second. In this particular case, because we want this to run in parallel, we're going to subscribe on a subscriber's scheduler. So this is a scheduler that's going to be used to actually do the observing. And in this case, as you can see, we're going to take the common fork join pool, which is essentially a singleton method that returns the one and only common pool from the fork join class. That's a static method, of course. And we make that the scheduler that we're going to be subscribing on. So we're going to be subscribing on the fork join pool. There's a bunch of other schedulers you could schedule yourself on. You could schedule on an I/O pool. You could schedule on basically a user interface pool or a computation pool. I'm using the common pool because I want this to be comparable with the other examples. Then we go ahead and take the observables, which are these images, these URLs, and we go ahead and apply the download and store image method, which in our particular case is just going to use the blocking task version that we'll look at in a second. So you'll notice that that looks pretty much identical to what we're doing here for parallel streams. The only difference is we used parallel stream here, whereas down here we did subscribe on, but it's pretty much the same idea. We're passing in download and store image, the apply method. Here we do the same thing for map. And then you'll notice that we use another mechanism built into RxJava called collect into. And what we're going to do is we're going to collect this stream of observables, which will now become a stream of file observables because they'll be transformed by download and store image apply method. We're going to basically store that into an array list, and we're going to add each element into that. And that will end up with a single array list of objects, which of course will be the files that we downloaded. And then we're going to go ahead and run blocking subscribe, and I'll talk in a second about what that is. But basically, the final method in an observable chain in the RxJava model is some type of subscribe method. And subscribe is what sets the wheels in motion. Just like with parallel streams, collect is a terminal operation that starts everything running. So too in RxJava is subscribe a method that starts everything running. So that will begin to basically have the items pushed from the observable, and it's from iterable factory method, through the list of transforms in parallel, collecting the results into an array list. Now, what we do here is we end up getting this image files list, which is pretty much exactly like what we got up here with image files. It's just that the syntax is a little different for RxJava. And so we go ahead and take those image files and we go ahead and print them just like we did up here. So that code is pretty much identical. Now you may ask, why am I using blocking subscribe? And the reason, of course, here is that this program needs to wait for the processing of the stream of URLs to transform and be downloaded and stored in files to finish before we want it to continue on. And there's various ways to do this. I could have put a sleep after this and so on, but that's kind of busted. So I used blocking subscribe. Now, if anybody is a crackerjack RxJava programmer and would like to suggest a better way of doing this, I am all ears. I'd love to see a suggestion of a better way to write this code. But that's what I came up with based on the learning I've done thus far with RxJava. Let's take a look at some of the other methods. Here's download and store image. All this does, as you can see, is it takes a URL, it downloads the image, and it stores it on the local device. And this particular implementation does not expand the pool of worker threads in the common fork join pool. So that's kind of the default behavior. And if you go back over here and you look at run, you'll see that that performs rather dismally. It doesn't perform very well. And that's because it doesn't expand the pool properly. Let's take a look at some other implementations that do a better job. So here is download and store image using the managed blocker mechanism. This is that super cool feature that's built into Java 8 and beyond's common fork join pool that will automatically increase the number of threads in the common fork join pool when blocking might occur. So you can see what we do here is we take the URL that's passed in, and we have to do this somewhat sleazy little trick for reasons you'll see in a second to make an array of one element. That's very sleazy, but you'll see why we have to do it in a second. And then we go ahead and we use the managed block method on the fork join pool. This is a static method, of course. We make ourselves an anonymous inner class, which is an instance of managed blocker. And we define the block method on this to download the image and store it into the first element, the 0th item in the image array. And we have to do this because of the way that basically anonymous inner classes work with respect to accessing variables that are defined outside of their scope. Again, there are better ways to do this. I will show you a better way to do this in just a moment. So this is the implementation that we provide. You can see we also have this is releasable, which always returns false. I won't go into that right now. My tutorials on my website in my digital learning repository have lots of information about managed blocker and how to program it. Okay, so basically you can see here what's going to happen is the managed blocker object we create will be passed to the managed block method. And if something blocks, which of course it will in this case because it's going to be downloading a big image over a relatively slow link, because all links are relatively slow these days because everybody's staying at home doing Zoom meetings. This will end up basically creating a new thread, or the fork join pool will create a new thread and put it in the common pool. And we'll see how that works. In fact, if you come over here and you take a look at the result here, the test adaptive MB download behavior method, you'll notice that it has more threads than the default. The default only used 8 threads because that's the default size of the common fork join pool. But by using the managed blocker, we basically end up with a pool of threads that grows to correspond to the number of images that we have downloaded here. Now, were we to wait a little while, that pool would go ahead and gradually contract because that's the way that the common fork join pool works with respect to managed blocker. Managed blocker adds a thread, and then when it's not used for, say, after a minute, it goes ahead and terminates it. So it grows and shrinks adaptively. And as you can see, the adaptive MB download behavior is faster than the default behavior, which is slower. And the main reason for that, of course, is we have more threads. And when we have more threads, if those threads spend a lot of time blocking, other threads in the pool can be downloading in parallel, leveraging the inherent parallelism we have on our multi-core processor more effectively than we had we restricted the number of threads to the default size. By the way, that's a very important thing to understand. A lot of people don't understand that you can use the common fork join pool for IO-bound processing, as we're doing here, just as nicely as you can use it for computation-bound processing. There's actually some mysterious documentation in Java that gives the impression you can't use it for I/O, but you can. You just have to know about this managed blocker mechanism. Okay, let's now go and take a look at the next example. This is download and store image BT, where BT stands for blocking task. And unlike this mechanism, which I think you'll agree is somewhat sleazy and ugly because we had to write an anonymous inner class, this mechanism is nice and clean. We use the blocking task call in manage block method, and we pass in a supplier lambda that says, download this image at this URL. And as we'll see in a second, call in manage block encapsulates the manage block API with a nice clean Java wrapper, C++ on the brain. Down here, you can see the download image method. This is the one that they're all calling. And that just goes ahead and calls into netutils download content. And if you go look at netutils, you can see it's got this method in here called download content. And all this basically does is it uses get input stream, passing in a URL, and then it reads the contents into a buffer and then writes it out and makes it be big enough to store everything that we need. Okay, so that's just showing kind of what's going on under the scenes. But obviously, that's a blocking call. That's the key thing. So let's go take a look here at BlockingTasks. BlockingTasks is really cool. BlockingTasks is a nice little wrapper that encapsulates the underlying managed blocker mechanism with a nice object-oriented facade. So here's what it looks like. You can go read this Stack Overflow link to learn more about this particular approach. I shamelessly was inspired by what was there and did a few things on my own to make it a little cooler, but it's basically what's there, and you can read about the pros and cons of this approach. So here is the class. It's a utility class. Because it's a utility class, I probably should have defined it to be final, but I made the constructor to be private, and it's only got static methods in it. And you can see here the main method is the one called call in manage block, which takes a supplier. It's a static method that's parameterized. And this supplier goes ahead and makes an object of a nested class, defined down here, called supplier manage blocker, which encapsulates the supplier, stores the result into a managed block object, and then passes that to the fork join pool manage block method. And then when it's done, after it's finished doing the work that was in the supplier passed to it, then that will return, and then we'll get the results from the managed block variable. There's also a runnable version that doesn't return any result. So let's go take a look at supplier managed blocker, which implements fork join pool managed blocker and stashes away a few fields. It stashes away the supplier, keeps track of the result, and keeps track of whether or not we're finished. Here's the constructor. You can see the constructor just stashes the supplier away in the field. We called that up here. And then you'll see that there's a block method, and that's the method, of course, that's going to be called when we pass the managed block object into the managed block method. And the block method, as you can see, just says, hey, supplier, go get me the result. And of course, what get is going to be calling in this case is it's going to be calling this Lambda supplier. So it's calling download image URL. That's what gets passed in there. Remember, when you pass a Lambda, it doesn't get run right away. It gets squirreled away and used when the get method is called. So that's the way that suppliers work. That's also another example of a functional interface in Java 8 and beyond. I have a whole pile of videos that talk about functional interfaces. They're also in my 2019 parallel functional programming course. So feel free to take a look at that. And then when we're all done, we go ahead and have a helper method that returns the result that we got from getting the supplier. So that's all going to be done in the background. And there's also a runnable version of this as well as a supplier version of this. So I think you'll agree with me that this wrapper is very cool. I think you'll also agree with me that this code is a lot easier to look at than this code, which is too low level, if you will. Anonymous inner classes are always questionable, and this greatly encapsulates things and works much nicer. If you look at the runtime performance, you can see it's a little slower, although I'm not sure if that's really something that is a function of using that wrapper versus just the inherent non-determinism of downloading large images over a shared network during business hours. The last thing I want you to notice, though, I think this is interesting, is you'll notice that no matter what, the RxJava version performs rather poorly. And I need to go back and spend some more time fiddling around with this to understand why. Maybe I'm not using the right pools. Maybe I'm not using the right methods. So if somebody here is an RxJava guru and wants to come back and show me a better way to implement this, I would be all about it. So hopefully that can give you something to work on. So that was basically what I wanted to talk about. Oh, I do want to show you one more thing. Here is the clever timer class. This is what I use to run the tests and to time them. So you can see up here, I call the runtimer.timeRun method, and I pass in this case, a runnable and a name. So let's go take a quick look at run timer, because that's pretty cool. Run timer maps the name of the test to the time taken to do the computation. It keeps track of the start time, and it keeps track of the execution time. Basically, the method that we have here is called time run. This is the one we're actually using. So what we do here is we are going to go ahead and start timing. Then we take the runnable and we call its run method, which, as you can see over here, just turns out to be this lambda expression that we pass in. So we go ahead and run that test. Then we stop the timing. And then we take the test name and we take the execution time and we put it into the results map. So that's how we do a timed run. And then down here, there's a method here called get timing results. And you'll see that when I run this thing, somewhere at the bottom of all this, I print out the timing results. And timing results is pretty clever. It creates a string buffer, and then it goes through the results map. And keep in mind, the map is going to be a set of map entries that map the key, which is the name of the test, to the time it took to execute, which is the long. We convert that into a stream. Then we go ahead and we sort that stream by using the comparing by value method on the map entry. So now we have a stream that's sorted by the value field. And then for each element in the stream, we go ahead and append to the string buffer the key, which is the name, which, as you can see here, would be test adaptive MT download behavior. That's the key. And then we go ahead and print executed in, and then we print the value. So this is how we get that output. And that's how that output is ordered. And the very last thing we do is we convert the string buffer to a string, and we return that as the parameter from the get timing results method that's defined on the run timer class. And I'm sure there are better ways to do this. If someone has a better, more clever way of doing a little timer, again, I'd be happy to learn about that. But this is just my easy way of being able to set up a little timer test, run the test, and then you can see here it's real simple to just encapsulate each of my calls with a little lambda that will then get executed in the appropriate context and store the results. So that's basically what I wanted to cover today. What I'd like to do now is I would like to go ahead and take a look at your questions, and we'll spend some time on that. Okay, so question number 1 is a good question. It asks, what are the consequences of not calling warmup? So the consequences of not calling warmup is that whatever test runs first will end up having to create the threads in the common fork join pool. Now, if you're doing enough processing, and we're doing an awful lot of processing here because it takes a while to download those images, probably not a big deal to have to pay the cost of warming up the thread pool on demand, which is what would happen when we ran the first real test. But if we were doing less intensive work, like short amounts of processing, then whatever test we ran first would end up being penalized because it would appear to be much slower than it really was because it would have to pay the costs of creating the threads in the pool. The threads in the common fork join pool are actually not created until the first time the fork join pool is used. And it's basically created lazily on demand. So that's just something to be aware of. Let's see, next question. Do observables also emit in the fork join pool or only the code downwards? It should be emitting in the fork join pool. If someone knows a way to get them to emit faster, let me know. But that was my understanding using subscribe on in that manner. But I'm still in the process of learning RxJava. So if someone else has a better way to do it, please let me know and I will update the tests. I'm not trying to cast any shade whatsoever on RxJava. I think it's really cool. Another question, image does not seem to be protected by any synchronizers. We don't need to protect it because each of these calls is being done in a separate thread in the fork join pool, and therefore there's no cause for concern with race conditions. It's local to that method and therefore will never be shared. Is it advisable to use manage blocker for indefinitely blocking tasks? Well, what you can do is you can conceivably run into problems in that case where you would end up, growing the number of threads in the pool indefinitely. So you need to be careful. If you read that link in the blocking task class that talks about the blocking task wrapper, it talks about the pros and cons of using Managed Blocker. So Managed Blocker is not a panacea, but it works very, very nicely for these kinds of programs that have a bounded number of I/O intensive operations to perform. Is there any reason why Runtimer is not declared to use concurrent hash map? I could certainly use it to use concurrent hash map. The way it works for my particular case, however, is I don't actually ever call it concurrently. Each test runs. The test runs concurrently in either the fork join. Well, it always runs in the fork join pool, either using parallel streams or using RxJava. And I only print the time after everything finished running. So it's only ever called in a sequential way. Having said that, one of the things that would be easy to do would be to parameterize the type of map for Runtimer with some map API in the constructor. So you could either make it be a hash map or a concurrent hash map or a synchronized map or whatever you'd like. What's the difference between subscribe on and blocking subscribe? Why do we need to use subscribe on? The reason we use subscribe on is because by default, the way things work in RxJava is everything works in a single thread. And so there's one thread by default. If you don't want that, then you have to subscribe on a pool of threads. And so that's how you get concurrency and parallelism in RxJava. Not unlike the way that streams works, where by default, if you say stream as the factory method to convert your collection to a stream, it's sequential, runs in one thread. But if you have a parallel stream factory method, it'll run it in a parallel stream. All right, let's see. There are probably some more questions. Great. Well, those are the questions I got so far. If you have any other questions, please don't hesitate to ask them. What I think I'm going to do is, once again, share my screen, and we'll talk about some other things that we may be covering next. And this may give you a chance to think about some more questions to ask. So this is my live lessons GitHub repository. By the way, I also have a ton of other GitHub repositories. So if you go here to my main GitHub link, you'll see that I've got lots of repositories. I have repositories for C++. I've got repositories for pattern-oriented software architecture, the courses I teach at Vanderbilt, all the programming assignments and slides are available through those links. We'll talk more about that in a second. Parallel functional programming. I teach a MOOC on Android app development. So there's lots and lots of stuff here that you might want to poke around with. Many interesting things I've done over the years. Live lessons is where I typically put the code I'm working on that I'll be presenting in my tutorials that I give. So lots of interesting stuff here, lots of fun stuff in the Java 8 folder. And there's a little README file in here that explains what all the different examples do. I think we're probably going to talk tomorrow, since people seem to want to hear more about completable futures. I'll show you this really cool example that uses completable futures to search, to traverse a nested hierarchy, either on your local computer or in the World Wide Web through a web server, and then recursively count the number of images that are reachable from some root URI. And this is cool because it shows off some awesome completable futures features. And one of the next things I'm going to probably do is convert this example to use RxJava. And so we'll have some fun showing the completable futures version of this. We'll also show how to do it with RxJava at some point. But there's all kinds of cool examples here. And we'll be talking about these examples, I'm sure, in other sessions here. Lots of other stuff. Just if you take a look, you'll find many things. If you go back over here to my Modern Java by Example webinars page, you'll see I give some links to other places to go. I have a Facebook group here on Java concurrency. Feel free to post any questions you think of that we didn't get to on that Facebook page. Feel free to subscribe to that Facebook page if you'd like. It's a group. Then I have all these videos that are available over here. So these are all the videos I have for the classes. This is the course I teach at Vanderbilt. I taught last semester. That was on parallel functional programming, and it's got tons of stuff on Java functional programming, like lambda expressions, method references, functional interfaces. We do streams, sequential streams, parallel streams, fork join pool, completable futures, and all the slides and the videos and so on are available there. It's probably about, 30 hours worth of stuff on just this page alone. There's also other things that I've covered in other tutorials as well. I teach a MOOC on Android app development. Some of you may have taken that. So if you want to learn how to do Android and do concurrent programming in Android, that's a good place to take a look. A couple of years ago, I taught a MOOC on parallel or pattern-oriented software architecture for concurrent and network software. And this is no longer available on the Coursera platform, but I put all the videos on my YouTube channel. And there's lots of good stuff here about gang of four patterns. And the examples here, by and large, are in C++. So if you're looking at a C++ way of doing things with patterns, there's lots of good stuff here. There's also a lot of tutorials here on the ACE framework, which I developed years ago, that's written in C++. I also have a bunch of courses available through Pearson's Live Lessons online training series. So I have one on Java concurrency, and it's basically about, I think about 9 hours of pre-recorded material on Java concurrency, both kind of classic Java concurrency with threads and synchronizers, as well as more modern Java concurrency. There's also one on design patterns in Java, which is covering the gang of four patterns primarily, but also some other stuff. And then I also teach a bunch of interactive live training courses that are done by O'Reilly on their Safari platform in conjunction with Pearson. And so I'll be posting those. I'll be having some new courses I'll be teaching in May on Java synchronization, on sequential Java streams and functional programming with lambdas and method references, as well as also design patterns. So lots of good stuff. Each different variant comes with different pros and cons, but you're welcome to poke around and do whatever you would like. Let's go back and see. I think a few more questions may have come in here. What does it mean that we say that streams are sequential and the completable future model is async? So sequential streams are sequential, sort of by definition, because there's only one thread. Of course, you can have parallel streams, and that will run in parallel. But parallel streams, by default, use a synchronous blocking model. Even though things run in parallel, it runs synchronously in multiple threads in the common fork join pool. Conversely, completable futures are asynchronous or more reactive in nature because the operations run asynchronously in the background, and they use this wonderful magic of so-called completable futures that get triggered when operations complete. So we'll talk more about that when we talk about completable futures. Again, if you want to learn more about all these topics, go take a look at my parallel functional programming course. Tons and tons of stuff there that will talk about that. Let's see. The question here is, even the parallel stream runs in a fork join pool. Yes, that's correct. But by default, streams are sequential because there's only one thread. But keep in mind that that's a different model. Parallel streams, by default, use a synchronous model, whereas completable futures use an asynchronous model. And for more information on that, again, go watch those videos. I cover that in enormous detail. It's also worth noting that the sequential streams could be nicely combined with completable futures to give you a very full-fledged reactive programming model. It's actually quite a bit like RxJava in a lot of ways. So it's asynchronous, and it's also able to be done in a streaming style way. Again, watch those videos for more about that. Are there any APIs in the managed blocker to automatically interrupt threads if blocking tasks block longer than the threshold? No, you would need to write some code that would do that. You could write some kind of thread interrupter Would be a little tricky to do that, but it's possible. What you could do is when computation started up running, you could register it with some kind of monitor that would run in the background in some other pool of threads, perhaps, or just in some background thread. And if a thread ran for too long, you would go ahead and shut it down. But that is not what comes out of the box with Managed Blocker. Okay, well, I think there were lots of good questions. Thanks to everybody for coming today. And if you have any questions whatsoever, please don't hesitate to ask them. If you're curious, go ahead and post them on the Facebook group if you didn't have a chance to ask your question, but you think of something later on. And what I'm going to do later, and later is probably later this afternoon, our time in Nashville, I'm going to go ahead and I'm going to upload the video of our discussion, and I'll stick it in my YouTube playlist here, which is the Modern Java by Example Webinars YouTube channel or YouTube playlist. So everything will be up there. You're welcome to come back and take a look at what we did. I will record these videos and put them up every day. And hopefully in the not too distant future, we'll have a nice collection of material that you can learn from. Also, like I said, I'll be posting the next topic that we'll be covering on my website. Tomorrow, we'll be talking about completable futures. So please feel free to join, and I will look forward to talking to you guys again soon. Thanks very much for attending.